we have been talking about the kinetics of chemical reactions, and the main tool through which we were studying chemical kinetics was concentration. But here I have a problem that involves gases, and the problem gives the pressure of the container or the vessel in which this reaction, the decomposition of dinitrogen pentadioxide, is taking place. Now, if you want to approach a problem like that, let's first read the problem. So here is the reaction. Gaseous dinitrogen pentoxide converts into dinitrogen tetroxide and oxygen gas. This is a first order reaction. It's given in the question. And at time when the reaction has just started, initially the pressure of the container, let's suppose this was the container in which all the gases were kept, and initially there was just N2O5, and after some time there is still some N2O5, but other molecules of N2O4 and oxygen are also getting formed. So there is some change in the pressure due to that, and we have to calculate the rate constant for this reaction. So let's begin by writing some numbers. So 2N2O5 goes to 2N2O4 plus O2. Now, initially, I will write I for it. Initially, let's say the pressure of the vessel was 0.5 atm. That 0.5 atm was solely due to N2O5. So 0.5 atm here, 0 here, and 0 there. Now, as the reaction progresses, as you progress in the reaction, the change that occurs, let's say that if 2 moles of N2O5 have decomposed, then there is a pressure decrease of minus 2x. And if 2 moles of or 2 units of N2O4 have been formed, there is a pressure increase of 2x. And similarly for O2, there is just one molecule. For each 2 molecule unit of N2O5, there is just one molecule of O2. There is an increase of plus 1x in the pressure of O2. Now, if you sum it all up, as in the end, you have 0.5 atm minus 2x, the pressure of N2O5. The pressure of N2O4 is 2x, and the pressure of O2 is x. Now, one more thing has been given. So let's say that this change is for 100 seconds, and you need to figure out what x is. Because by finding out x, you clear out a lot of things. So firstly, you know that at 100 seconds, the pressure is equal to 0.512. So that means that the sum of all of these partial pressures is equal to 0.152 atm. That's what Dalton said. That's what the Dalton's law of partial pressure says. You add all the pressures up and it will give you the total pressure. Now, if you solve this equation, you have 0.5 atm plus x, these two cancel out, so plus x equals 0.512 atm. Now, once you have done this, you figure out what x is. So x is equal to 0.512 atm minus 0.05 atm, 0.5 atm, that's equal to 0.012 atms. And if you want to now figure out what the rate constant is, so remember we were talking about rate constant and time of the reaction as in the following expression. So Kt equals the natural log of the concentration at time t over the initial concentration. And the other way you could have written this, because you can use log tables that way, is you could also have written this as 2.303 times log to the base 10 of A at t over A naught. Now let's try using the second form of this equation. So notice here we don't actually have there is a negative sign there as well, sorry. So the negative kT, I just forgot that. Notice that we are not taking the concentration in this regard. In this problem, we just have pressures, only have pressures. And because you're having pressures, you need to do some sort of manipulation, and the way you do that is, instead of concentration, and this is the point where it gets a little bit tricky, you just put pressure. So now you write that kT equals negative of 2.303 log 10 of pressure at time t over the initial pressure. And notice this pressure is not the total pressure, This is the partial pressure. This is the partial pressure of the reactant, the partial pressure of reactant. And the reason why we do so is because the pressure, the partial pressure of a gas and its concentration within some sort of system are related, and more on that is in some other videos. But for now, let's ease this discussion down a bit. And so in this case, we are having the gas N2O5. So that means that now we need to plug in some numbers. So let's try. So k is unknown, that's what we need to figure out. Time t. So time t is 100 seconds. 100 seconds, that's what we are given in the problem. We are talking about 100 seconds here. We know 2.303, we know log 10. Pressure initial pressure of N2O5, we know what that is. The initial pressure of N2O5 is 0.5 atms. So now you write, let's write the modified equation. So k times 100 seconds equals 2.303 log to the base 10 of, instead of p naught, you write 0.5 atm. Now what is the pressure at 100 seconds? What's the pressure at time t equals 100 seconds? Well, the pressure is 0.5 atm minus 2x. 0.5 atm minus 2x. So 0.5 atm minus 2x. Now instead of x, we do know that the value of x is equal to 0.012. So instead of x, now you can write 0.012 atm. And if you solve that a bit, so you would then arrive at k times 100 seconds equals negative 2.303 log to the base 10 of 0.0. So if you subtract that, I'm not doing the subtraction here, you would arrive at 0.476 atms over 0.5 atm. And now what you can do is you can solve for this equation. You can find the log. You would use a calculator, use log tables, do whatever you have at your hand, and you would arrive at k times 100 seconds is equal to negative of 2.303 times instead of the log, if you calculate this, ATMs cancel out. If you calculate the log, that is equal to 0.0216. And so that means, now there are no units here on the right hand side, so k is equal to there is also a negative sign there, by the way. So the two negatives just cancel out. So k is equal to 2.303 times 0.216 over 100 seconds. And you could also have done this by hand, use a calculator or something. And you would arrive at 4.98 times 10 to the power negative 4 second inverse. And in general, you can apply this strategy to any general reaction that you have at your hand. So if you have a reaction, A gas going to B gas plus C gas, and let's develop some strategy for a general reaction. Initially, let the pressure be pi atm. Not we are not specifying the units here, and for the products there is no product, so the pressure is just zero. The partial pressure is just zero. The change is if 1 mole, let's assume that there are just one here. If 1 mole of A is used, then there is a change of negative x in the pressure, plus x in the products, in both the products. If there would have been, let's say, some other stoichiometric coefficient, so if there would have been an ma, where m is any number, let's take 2a. So if there were 2a, you would have written negative 2x. If there would have been 5c, you would have written plus 5c. So you get the idea, right? And let's just do it when the stoichiometric coefficients are 1. So in the end, the pressures are pi minus x, and x. Now, if you are given with what's the final concentration at whatever time, at time t, let's take capital T here, just to avoid any confusion. So at time t, the total pressure of the system is P total. And then what you can do is you can cancel these x's out. So you have pi minus x equals P total. And that means that x is equal to pi minus P total. I just messed it up. So it would be pi plus x equals P total. So x would be equal to P total minus pi. There have been a few mistakes in this video, but anyways, once you have figured out what x is, what you can do is you can refer back to the equation that we had. So kt equals negative of 2.303 log to the base 10 of pressure instead of concentration. I was going to write the concentration, but we would write pressure at time t over the initial pressure. And now instead of small t, you would write capital T. So K capital T equals 2.303. This negative sign would flip the log here. So log to the base 10 of P naught over P at time t, and P at time t, this partial pressure, Pi minus Px, this partial pressure, P at time t, is equal to Pi minus x, and Px you write P total minus Pi, and that is equal to 2Pi minus P total. And you plug that in right here, and in the end you would arrive at kt equals 2.303 log to the base 10 of P naught over 2P minus P total. And one thing that we also need to substitute is that the initial pressure here, we took it to be Pi. So instead of P naught, you also write Pi. So there have been a bit of arithmetic mistakes, a bit of manipulation mistakes, but overall you get the idea. And now you're equipped with all the tools that you need to tackle reaction rate problems that involve pressures. And the idea is just that instead of writing concentrations, you would write the partial pressure of the reactant. I hope this video helps. See you in the next one.